Well, I'm sorry to say that Dr. McLean, she couldn't make it, so I'm going to do the presentation. So Salt Cedar, um, I'm not sure I can tell you a lot of information about this planet. You already know more than I do. I'm not an ecologist, just to so be gentle. and The objective of this presentation is to illustrate the use of a tool we developed called the Riparian buffer delineation model in assessing whether salt cedar is located inside or outside the riparian corridor to aid restoration efforts by producing very accurate riparian boundary mapping, and can provide inventory for your riparian areas. A little background about the tool. My advisor, Dr. McLean, she took the project as a 6 month project, and after 6 years, she graduated a master's and a PhD student from the project. But we were successful in developing a tool that's available for download and for free. When I started on the projects, I was shocked about the number of riparian definitions. I come from engineering. Everything there is a solid fact. 1 + 1 = 2. It's not the case when you work with the riparian definitions. Then after that, I found another paper that lists 35 terms for just the word riparian or riparius. So I was thinking maybe I should drop off, go find a job. So then after that, we settled on a definition introduced by Elhart and Sandivari, which is the three-dimensional space of interaction of riparian areas. It's a very long definition. But we saw from the literature that all the riparian methodologies to map riparian areas doesn't take care of the floodplain. Yeah, it goes on the stream and like fix with buffer, but doesn't take care of the water course and the floodplain. We adopted the 50 years flood height or the 50 years floodplain as the hydrological descriptor of our model, as Elhart suggested in his work, and also Sandivari, because it intersects with the first terrace, and it's better than using the 100 years flood height, which overlaps with a lot of uplands and gives you sometimes an overestimation of your riparian areas. And our objective when we developed the tool is those sets of objectives. We wanted a simple, practical tool that everybody can use with a little experience in GIS. At the same time, they should use open source geospatial data that's available. So we don't need to reinvent the wheel. I mean, it's very easy. I can tailor a model for a specific project area and tell you, okay, this is how I map riparian areas, but you need 1, 2, 3, 4, a long list of data to do that, and the model will be useless if I want to map another study area in another state. We introduce a set of optional data that, like a National Wetlands Inventory and the Sergo digital soil data, to aid in the riparian mapping. The model is just simple ArcGIS tool that you can share, and the results can be replicated and can be compared across the United States. As I said, it's a simple ArcGIS tool. You can attach it to your ArcGIS software. It works with all ArcGIS softwares till 10.2.2. This is the model interface. And it's a very simple interface. All the calculation has been done in the background of the model. Here I say it's 2.3. This is it's an old slide. The version I'm working on now and debugging, and we will release very soon, is the 3.0. You use a streams layer, and there is a streams criteria. So basically, you tell the model what kind of streams you want to delineate riparian area for. And we have the 50 years flood height that it's You can calculate it using a method that we provide with the model, or you can calculate it using any other method like HACRAS or hydrological charts or any other method. And here we have the sets of our optional data to aid you in mapping riparian areas. The inputs is all available on the internet, and it comes from reliable federal sources with known accuracies, and it's very well maintained databases. So we use the streams layer, the NHD streams layer. Um, some people, they say, okay, why use the NHD? There's a lot of positional inaccuracies in that. Okay, if you have the time to delineate your own derived streams network, okay, just throw it in the model. We'll take that. But I usually use the NHD, like for simplification. This is the 50 years flood height Excel file that we provide. It's a method been developed by Mason in 2007, and it uses the water USGS water data, gauge data, to calculate the 50 years floodplain. And it's very easy to use. We use the National Wetlands Inventory. It's available all over the United States. We use the Cirgo Digital soil data. And in this case, I'm using the first layer as a hydric soil, drainage class, and hydrological soil group to identify riparian soils. DEMs available, 10-meter DEMs all over the United States, and 30-meter DEMs. I don't use 30-meter. I use 10-meter. In the East Coast or eastern part of the United States, now there's 3-meter available by the USGS, and sometimes 1-meter available. And also they give you the LiDAR point cloud of those DEMs. So if you want to do more, clearing of the data, you can also do that using ArcGIS or even RDAS or any other software. And in the end, I use the National Land Cover datasets or the Core Plan Data Layer, CDL, produced by the USDA. So I just don't produce a dummy polygons of my riparian areas, but also I will throw some classification just to know what kind of land cover I have in that area. All the data can be downloaded from the USDA Data Gateway for free. Just have an account and you can start downloading the data. Since we're using like multiple data and resources in our model, you need to do some data preparation to achieve the best accuracy, mapping accuracy. So the hydrological estimation, I calculate the 50 years flood height, as I said before, using the USGS water data. And here, this is from a project I just finished in Michigan. This is the Hiawatha National Forest, eastern part, and this is the western part. And using this tool, I was able to produce a full riparian inventory for both parts of the national forest. And these are the gauges that are located in or around my national forest. I download the annual statistics of my gauge or the stream flow, which one is available. Also, I download the field measurements of my gauge. I plug my data here and there, and then click on my 3 sets of equations. I produce those charts, and then after that, I just plug the coefficients of my equation and I solve, and I use year 1 as a base, and year 50 is calculated, which is 1.42 meter for the eastern part of Hiawatha National Forest. The NHD, as I said before, first I need to make sure that the column stream level or the stream order is available within my NHD layer attributes table. And then the second thing I need to make sure of is the positional inaccuracies of my NHD streams. The NHD reported 40 feet. From my experience in the in the east part of the United States, it's okay. Sometimes it's like, 5, 6 feet away from the original location. But when it comes here to the west and southwest of the United States, oh my God, this is all I can say. Like, so this is in Idaho. It's a 1 meter DEM derived from LiDAR data. And I overlaid my NHD streams here in red. I don't know if you can see it. And this is actually my NHD location, and you can see the shift. And this is not the extreme case. There's some locations and the data that the NHD streams goes on top of the hill and comes down from the other side, which was like, wow, new physics. Soil data, everybody knows that soil data comes in two parts, spatial and tabular data. There is a very useful software from the NRCS. It's free too. And you can just attach your spatial part here and your database here, and then specify what kind of property you want to attach to your map units. And in this case, I'm using if I can see it, the hydric rating here, and then click on map, and this will produce those layers on the fly. So then, before running the model, you need to make sure that your file geodatabase is prepared like this. You have DM, 3 layers of your soil, lakes layer, NLCD, NWI streams, and watershed layers. How the model works is basically like, in simple words, I don't want to be very technical. I place sample points, the green, at 75% on, and the distance between those sample points is 75% of my DEM. In this case, I'm using 10-meter DEM, so I'm placing a sample point at 7.5 meter. Then around each sample points, I produce those transects. The length of those transects you can control with this length of transects distance vector, and you can sample away from the stream at 3,000 meter, and it's been capped to 3,000 meter just to optimize the processing time. I personally, when I developed the model, I went to 5,000 meter, and ArcGIS didn't crash, but I said, okay, 3,000 is enough, especially like in Michigan. And then we run those 11 transects around my sample points. Again, the distance between each transect points is 75% of the DM spatial resolution. And this is just for illustration. If I run those transects on all over those sample points, I will produce a point cloud like this. In this case, I'm using a 200 meter here as my sampling distance away from my stream. So I'm producing 26 transects in each vector. Then I use the 50-year floodplain as my threshold to locate my riparian boundary. Then there's some set of geospatial tools to refine the results. We ran this tool on this part of the Rio Grande River called, I think, the Forgotten River, because we saw some classified raster that classifies salt cedar in this area. And the classified rasters were produced by the Mid-American Geospatial Center at the University of Texas, and they used Landsat 7. This is their, they use like 4 sets of salt cedar land cover classes, and their newest one is this one that produced salt cedar map from Landsat 8, and this is from 2014. So we ran the tool on this section of the Rio Grande, and this is the red is our delineation for riparian areas using 150 centimeter. And I used that just for illustration. I didn't calculate the 50 years flood height at that area. Just wanted to see how the model performs. Then after that, you can look at these areas that have been included in my delineation here and here. Then I said, okay, there is a gauge just north of my study area. I will calculate the 50 years flood height at that gauge. And turned out it's 90 centimeter.
Test.
And sees like it includes 98 of the cedar classified in that part of the Rio Grande is within the riparian area. And you can see when you use the 50 years flood height, the accurate 50 years of flood height, you hello. So if you use the 90 centimeter as the calculated 50 years flood height, you can see you achieve more accurate mapping, and there's some external extra areas were not included in the mapping. And it performs very well. And still, there's 90% of salt cedar within those riparian areas. In summary, this is a very simple tool that land manager can use to map variable with riparian areas. It uses open source geospatial data, so it's basically zero cost for the data. If you want to acquire, high resolution data, it's your problem, but I think you can live with those. You can produce base maps for your riparian areas, and then overlay those base maps on any kind of remote sensing data and extract that data. And this is actually what I do now in the Hiawatha National Forest. After I produce those base maps, I overlay that on Landsat 8, and then I extract that portion of riparian areas, run eCognition, segment all my riparian areas, and come up with a specific riparian land cover classification. It's very faster. It reduces dimensionality of my data, and it will enhance my signal to ratio noise data too. And since I have like few minutes, there's some technical issues I didn't include in the presentation because of the time, but basically the model is very sensitive for the 50 years flood height and very sensitive for change in elevation. The second parameter that affects the results is your DEM. The higher spatial resolution of your DEM, the better riparian mapping accuracy you will achieve. I did a study in Idaho, and I used 1 meter DEM, 3 meter, 5 meter, and 10 meter DEM with, and all the other parameters are constant. And I saw that there is increase in riparian mapping about like 4% between 10 meter and 1 meter DEM. And with that, this is all the literature you can download and look at the tool if you like, and if you have any questions. Thank you.